Good morning. A little bit of a late start there. It's 11:13 now. Again, another nice morning in Toronto. So welcome everybody. I've just posted the pre-class slides, so sorry about that. Totally slipped my mind. Let's share screen. Let's see what's on the menu here. Okay. And also I want to put my participants and my chat. Okay. So today we're talking about friction. This is showing two surfaces that are close together, and they're always, any surface, no matter how smooth it looks, will have microscopic little bumps and divots and things, holes. And so when you put two surfaces against each other and you try to move them sideways, you get what's called friction. And I want to give you some tips for this chapter 4 pre-quiz that we've got going on today. I'm still not seeing the participant list. Try that again. My Zoom can be a little slow. Here we go. There are 578 people on the call, so that's probably what's slowing me down a little bit. Okay, so I'm gonna put up attendees. Could I speak louder? Okay, hopefully you guys can hear me. And maybe there's a volume issue, I'm not quite sure. Okay, good. So moving along, there's a chapter 4 pre-quiz, which is worth 16 homework credits, 16 homework. Remember, these are the optional credits that you're getting a lot of from Mastering Physics. Well, there's 16 of these for these little pre-quiz. The way it goes is that this will be the exact same format as midterm assessment 2. Midterm assessment 2 will be completely different than midterm assessment 1. Midterm assessment 1 you did last week was multiple choice and was marked automatically by Quarkus. Midterm assessment 2, which is coming up on, I believe it's October 12th, it's a Tuesday. It's at the same sort of time, Tuesday night, starting at 8:10, but it will be 2 written questions. So what you will have to do is click on this answer template sheet. You can download that right now. That's what you're going to need for both this quiz and also midterm assessment 2. And then you could print it out, write out your solution, take a photo in good light, and then just go on the q.utoronto.ca and just upload the photo. That, I think, is probably the easiest way. The tablet method would be that you have some way, like I happen to have this little tablet thing, you have some way of writing directly onto a PDF. That's fine too. And then you can just upload the modified PDF to the question. You may only upload 1 file per question. It should be a full image of your written solution on one side of the paper, as per the answer template sheet. So the answer template sheet has all these steps in it, 4 steps: the sketch and translate, the simplify and diagram, represent mathematically, and the solve and evaluate step. To be awarded maximum credit, you must show each step in the problem-solving strategy clearly, completely and correctly. You may earn up to 2 points per step for a total of 8 points per question. And so there's 2 questions, that's why it's out of 16. And this is all going to be marked by actual TAs. I'm hiring a bunch of TAs that are going to go through and mark all 850 of you. So they'll look at your actual solution and judge it. So in the sketch and translate phase, what you have to do is sketch the process, label the physical quantities, and identify your unknowns. If there's Newton's laws, you should identify what the system is. In the simplify and diagram phase, you should identify what your simplifying assumptions are that are necessary to solve the problem. When you're using kinematics, you should make a little motion diagram or some position time graph, for example. If you're using Newton's laws, which you will be for this midterm assessment and the quiz, you should construct a force diagram. And this is one of the rules. Force diagrams must include labeled forces with the 1-on-2 subscripts, where 2 is always the object that you're considering, the system. And 1 is always one of the external objects that's providing the force. For example, for the force of gravity on an object O, you could label it as F sub G, and then in the subscript E on O, where E stands for Earth. Okay, that's important, and it'll be part of your mark to do that. And then the represent mathematically step, you use those forces and clearly apply the relevant physics model to relate the known physical quantities to the unknown quantity you wish to solve. In other words, you set up an equation and solve for the thing you're trying to find. And in this step, you may drop the 1-on-2 subscripts just to make the math a little easier, so you don't have to always write them. And then in the solve and evaluate step, you substitute the known values for your actual numbers, plug in the numbers, work it out, indicate your final answer, and you must evaluate your answer by comparing its magnitude with something else, or just checking to see that the sign and the units are reasonable. Okay, that's your little pep talk. Let me look at a couple of things up here on the chat. So this chapter 4 pre-quiz is available to take right now. I might just leave it a little bit more last minute. Chapter 4 pre-quiz, I don't think it has a time limit, but once you start it, I think you have to finish it. I didn't want to allow multiple attempts because I don't want multiple images to be uploaded, or else the TAs are going to be going crazy. Trying to click through all the images. They're going to have 850 of these to mark, so gotta be a little careful. Yeah, will we have extra time to upload our answers during the midterm? No, it's gonna have to all be uploaded once again within this 30-minute window. Once you see them, you've got 30 minutes to write it out and upload. It's also 30 minutes. So that's the midterm assessment 2. This one, chapter 4 pre-quiz, doesn't have a time limit. You can take your time, but it would be a good idea to time yourself and figure out how much time does it actually take to just click upload and upload the image. I would hope it wouldn't take more than a couple of minutes. The question is, will midterm 2 be 2 questions? Yes, it's the exact same format. Chapter 4 pre-quiz and the midterm assessment 2 are both 2 questions. And for both of them, it's the exact same rules. You just upload 1 page, which is you write on that answer template, same answer template. And midterm assessment 2 is only on chapter 4. Looking at all these questions coming in. And yeah, so you're being marked much more on your process and that you're following these rules of all these 4 steps than on the final answer. The final answer is worth like 1 point out of 8 for each of these questions, right? It's part of the solve and evaluate. All the other 7 points are based on you going through and showing all your steps properly. Make sense? That was good to get you guys to go through the steps and show your working and have a chance to demonstrate that you're following these rules, understanding the method that's outlined in the textbook, and writing these things down. Okay, good. Maybe we got a little bit of time here. Look at some of the hands that are up. A lot of people have got. I used to do this in class sometimes in real life, where my hand would be up so long that the blood would be draining out of my hand, but because not all professors look. But, Ishmael, did you have a question?
Hey, Professor, can you hear me?
Yeah, I can, yes.
So I read through all of these, specifically, and I understand what each, answer templates require. However, I have a question about, the TAs that, because we students are individuals and we individuals will have different approach for, a question. And some of us may draw something like Picasso and some of us may not draw something like a Picasso. So what will happen then, and how will the TAs mediate different ways of resolving the question?
Yeah, that's a great question. So I can say that I trust my TAs. These are going to be careful people that are working on their PhDs in physics and have seen it all. They are necessarily expecting that every student is going to have your own way of solving this thing. No two students' solutions should be identical, because there's always so many ways of solving it. And like you say, not all of you have the same, drawing skills or something like that, which is fine. But you still should be, overall following these instructions, writing your 1-on-2 subscripts, putting in an evaluate, and getting the right answer. To get the full 8 points, you have to have done these things, and you may do it in your own way. There's not a exact solution you have to copy, for example, in order to get full credit, but you do have to present your results in this format, or present your work in this format, so that in order to get the full 8 points. It's your work, but you're doing it in the style kind of it, Kina. I hope that helps a bit. And just one more before I keep going here. I've got Siddharth at the top.
Hey, Professor.
Hey.
I just had a question. So have you guys at least, so the 30 minutes is to download, print, answer the question, and then scan it and upload it, right?
Exactly, 2 of them.
So,
but you know what, you don't have to download anything, because you can download it ahead of time. All you have to do is read the question. You don't have to download anything, right? Because you've already got the file in your computer before the quiz even starts. Does that make sense? It's
but so we can see the question before the quiz starts?
No, but you can download the answer template. The answer template for this chapter 4 pre-quiz is exactly the same as the answer template for the midterm assessment. So you've already got that on your computer, and you can download it as many times as you want.
Okay.
Then all you have to do is just read the question on the screen on your quiz and just write down the answer and upload it. Uploading is the only thing that you have to do during that 30 minutes.
Okay, I understand. Okay, thank you.
Those are great questions. And so great. I'm going to take one more. Musa?
Yeah, hello.
Hi.
Yeah, so I had a question, but you answered it. It was about if we can re-upload the PDF.
Yeah, you can upload a PDF or an image.
No, it was if I had a mistake and I wanted to change the PDF and upload the new one. You said we can't upload multiple images. So.
Yeah, please don't upload multiple images, or it's just going to totally overwhelm my TAs.
Thank you.
Be careful. Yeah, you're welcome. Excellent. Okay, so I'm going to continue on to friction. Time now is 11:27. I'm getting a little behind. Okay, friction. So 2 kind of questions that sometimes come up is, does friction always slow things down? And can friction ever speed things up? And I talked about this a little bit last class. And the answer for does friction always slow things down is no. So it is true that kinetic friction on an object from a stationary surface does always slow the thing down. Okay, because the kinetic friction force is causing it to lose energy. But there are other kinds of friction. There's also static friction. And sometimes the surface is moving. So if you imagine this mass that's like a flatbed on the back of a truck, it's just sitting there, and the truck starts accelerating away. Well, if that box doesn't slide off the back, then it's going to be speeding up. And the reason it's speeding up is because of the friction force from the truck onto that box. Can friction ever speed things up? Absolutely. In fact, static friction of the floor and the bottom of your shoes is what allows you to walk or to run or to speed up. Why does friction exist? Well, because at the microscopic level, nothing is smooth. So here you have the bottom of your shoe, and then the wooden surface. If you were to look very, very closely with a microscope, you would see that the bottom of your shoe had all of these, I guess, like stalagmites or something like hanging down. And then even the surface of the wood, even if it's polished, if you look at it with a microscope, there'll be all these little mountains and valleys. And you can actually get little molecular bonds that form between the two materials. This is represented as little springs. And if you slide an object along, you have to break these bonds. Or the actual things have to crash into each other, and you can smooth something out if you rub two surfaces together. And again, that's due to the friction. Okay. So then there's kinetic friction and static friction. So the book starts talking about static friction and then goes to kinetic. I find that to be a little confusing because static friction is conceptually more difficult for me to wrap my head around. Kinetic friction is the easy one, so I want to start with the easier one, kinetic friction. Okay, kinetic friction. This is the sliding friction of a surface on a moving object. So that's why I put surface on object, and the K stands for kinetic. Okay. So when two flat surfaces are in contact and sliding relative to one another, heat is created. I can warm up my hands by doing that. So where's that thermal energy coming from? It's coming from the motion. It's slowing down that relative motion. So many experiments have shown that there is a handy equation, that the kinetic friction force of the surface on the object is equal to this mu sub K. So that's some dimensionless coefficient. This is dimension coefficient. Times the normal force of the surface on the object. Okay, so these are relating the magnitudes in order to find the direction of the kinetic friction. Well, the direction of the kinetic friction is opposite the direction of motion of the object relative to the surface. So for example, this kid is sliding this way down the hill. That's his velocity vector. And so the friction force, kinetic friction force on the sled is opposite the direction of the velocity vector. That's why it's slowing things down. Let's do a little pull. A wooden block weighs 100 newtons and is sliding to the right on a smooth horizontal concrete surface at a speed of 5 meters per second. So the coefficient of kinetic friction between wood and concrete is 0.1. So that's been looked up somewhere. U sub K equals 0.1. A 5 Newton horizontal force is applied to the block, pushing it towards the right. What is the force of kinetic friction of the surface on the block, and including the direction? So I want you to take a look at that, think about it, how you would solve it, and then I'll go through drawing a force diagram. Okay, let's give it another 5 seconds. Click in. Thank you for clicking in. Until about 80% of you click in, and then let's take a look at the answer. And polling, share results. So 59% of you have answered B. So let me just draw the force diagram based on of the block. So here is the block. There's going to be a normal force, N, of the surface on the block. Okay. There's going to be this, I think since the velocity is that way, the force of kinetic friction, oh, let's not forget our little arrows, right? Force of kinetic friction of the surface on the block will be opposite the velocity. So basically, the velocity is to the right. So the kinetic friction force is to the left. So I can already cross out D and E. And then there's going to be this force. So what this is, when it says weighs 100 newtons, what it really should say is that the Fg of Earth on the block is 100 newtons, right? That's what weight means. The force of gravity of the Earth pulling down on the block is this Fg of E on B is 100 newtons down. So, and then what you do is you say that the sum of the forces in the y direction is going to be 0 because it's not accelerating up or down, and that's going to be normal force minus the Fg force. And so what that means is that the normal force equals F sub G, which equals 100. And so the kinetic friction force, and by the way, now that I've gotten past the force diagram step, and I'm now on my, represent mathematically, I've dropped all those annoying subscripts of the 1 on 2 thing, just because I don't really like writing them again and again. It's mu sub k times n, and so that's going to be mu sub k, or well, let's just write it out. We know that mu sub k is 0.1. Now we're on solve and evaluate. Oops. And we know that the normal force is 100. So you get 10. So it was B. So that's good. You guys got it. Okay. A lot of questions are being asked, or will we be able to see both questions or just one at a time? So the way it is set up is that you're only allowed to see one question at a time. So you see it, you write it out, you upload it, and then you see the next one, write it out and upload it. Okay. Professor, if we were asked to draw a force diagram, do we have to draw the forces that cancel out? For example, in this case, the weight cancels out the normal force. So the answer is yes, you must draw, if the thing is near the Earth, there must be a gravity force of the Earth on it. And so you have to draw that on your force diagram. It's important. In fact, it is important in order to be able to solve this question. Let's do an example where we actually work through all this stuff in the exact same way you're going to have to do it on the midterm assessment. We've got the time, it's 11:37. So I've actually printed out my answer template sheet so that I can write on the answer template sheet. And it's always the same. It just looks like this. It's blank mostly. It says answer template sheet. It's got sketch and translate and a line, simplifying diagram and a line. You just have to try to fit it all in there. So a slippery box of mass 5 kilograms. Let's draw it with my amazing drawing skills. I'm going to call it mass of the box is equal to 5 kilograms. Is pulled at a constant velocity. Oops, let's put that. V is constant, that's important, because that means that acceleration is going to be 0. And what that means is that the sum of all the forces is going to be 0. I like to write that stuff down to keep that in my head. Nothing's accelerating. Pulled by a rope, so there's sort of this 20 degrees equals theta. Above the horizontal. The coefficient of kinetic friction between the box and the surface, so here's the surface, mu sub k is equal to 0.03. So let's define the system as being the box. Define system equals box. Shouldn't forget to do that. I want to find the tension of the rope on the box. Tension of rope on the box. So that's sort of my sketch and translate. I've also noticed that this is pretty small. Most of these little mu sub k's or mu sub s's are more like a tenth. They never get up above 1, but they're usually between 0.1 and 0.5, or sometimes even higher than 0.5. So that's a pretty small one. So let's go to simplifying diagram. I'm going to just keep sort of, I can't really scroll on this PowerPoint, but I can do this one. So I'm going to draw it. So I'm going to have the normal force of S on B going upwards. I've got the tension force of the rope on B going up, and there's a little angle here. There's your theta. I've got the gravity force of the Earth on B acting down, and I've got the friction force of K of the surface on B. Okay, so they're all acting on B. It's a good thing to check that, because B, the box, is what you're drawing the force diagram of. But then it's coming from 3 different external objects, either the rope or the Earth or the surface. We also know that F sub K is equal to mu sub K times N, so that's important. This velocity is towards the right. That's why I drew the kinetic friction going towards the left. I'm going to define plus y is up and plus x is to the right. I'm also going to use at this step, I have to get the components of the tension. So if this is theta, and this is the tension in the y direction, and this is the tension in the x direction, then sine theta is t sub y over t. So that means that t sub y is t sine theta. And cos theta is adjacent over hypotenuse, it's t sub x over t. So that means that t sub x is t times cos theta. But now I have to go on to the next slide. Do significant figures matter for the Chapter 4 quiz and midterm term? Yes, absolutely. You're going to have to do your final answer. That's going to be one of the steps in the solve and evaluate is round it to the right number of significant digits, I think. I can go backwards to the previous slide here. That was this one. And now I'm going to go forwards to this one. And now I'm going to go to the next slide so that I can do the represent mathematically. So sorry about flying through this. I wish I could kind of scroll and have like the previous screen, but I can't really do that. So moving right along, the way I like to represent things mathematically is, where is it? It's not on here, but it would say, so 3, represent mathematically. Represent the math. Should be on your sheet, is I like to write the x component. You can do this any way you want, but I think for me, I like to make a little table of my x components and my y components. So there's the normal, there's the tension, there's the gravity, F sub g, and then there's the kinetic friction force. So that to me helps keep everything in my head, because otherwise it gets a little jumbled up. Now, and I have to go back and forth here, the normal force is in the plus y direction, and it has no x component. So when I write that in, I write it here and I write a 0. It only has a y component. The tension force is the one we already worked out with that little triangle, where I got t cos theta is the x component and t sine theta is the y component. The gravity is going to act downwards, so it's just negative the mass of the block times g. And the kinetic friction force is negative because it's in the minus x direction of mu sub k times n. And it doesn't have a y component. So when I sum all these things up, I get that the sum of forces in the x direction, going down that column, which is 0 because it's not accelerating, is t cos theta minus mu sub k times n. Call that equation 1. And the sum of forces in the y direction, which is also 0, is n plus t sine theta minus m sub b times g, which equals 0. So I'll call that one equation 2, I guess. So I've got 2 equations and 2 unknowns. What I'm going to do is I'm going to solve for n in equation 2, and then plug into equation 1 and solve for what we want, which is tension. So 2 implies that n is the mb times g minus t sine theta. That's solving equation 2. And now what I'm going to do is take that equation and go and plug it into the normal force there, and then solve it out for tension. And it does take a little bit of algebra to do that. I get that t cosine, you have to try to fit all this in, right? Equals mu sub k times mb g minus t sine theta, which equals, I guess now you got to distribute the mu sub k in there, because there's a t I have to bring out, minus t times mu sub k times sine theta. Gather all the t's on one side of the equation. You get that t times cosine of theta plus mu sub k times sine theta is equal to mu sub k times mb times g. So we're running out of room in this slide. So I'm going to go to the next slide where I'm going to solve and evaluate. Give you a minute to look at that. Also, I'll go backwards a little. So slide 3, slide 2, and slide 1. So I sketched it to find the system. I drew the force diagram. I decomposed the diagonal force into its x and y components. Then I represented mathematically. I tried to sum up all the x components and the y components, and I got this. And again, the exact way that you do that, the exact style that you have of this is up to you, but you do have to show this work, or else I don't know how you're going to get the answer, right? So at this point now I'm solving for t. I get that t is equal to mu sub k times the mass of the block times g divided by cosine theta plus mu sub k times sine theta. So it's equal to 0.030 times 5 kilograms times 9.8 divided by cosine of 20 degrees plus 0.03 times the sine of 20 degrees. So you have to plug all this into your calculator, and what I got is t is equal to 1.5174, and it should be newtons because it's a force you're solving for. Oh, and don't forget, these are all, well, that's 3, that's 2, 3, and this is 2. So it's 2 sig figs, or significant digits. So I would round this off to be t equals 1.5 newtons. Put a box around it. I will notice that this is a small force. 1 Newton is a very small force. It's the amount of force that's required to accelerate 1 kilogram. With net force is 1 Newton on 1 kilogram accelerates it at 1 meter per second squared. This is a small force, which is reasonable as the ground is so slippery. Surface is slippery. Because remember, I even at the very beginning, I noted that 0.03 is a pretty small coefficient of friction. So that's expected. Okay. Are we working in degrees or radians? Well, this question is given in degrees, so you're going to have to use degrees on your calculator to do this. And I'm going to post all these slides afterwards. Sorry, I'm going a little fast. I'll post them right after class. I want to move on when we got a little bit of time left to talk about static friction, and I've got a couple of poll questions. So when an object is in contact with a surface, but it is not moving relative to that surface, it tends to resist slipping. So the object and the surface kind of get locked together, and this creates a force on the surface of the object, which is perpendicular to the normal force, and it's called static friction. There is no general equation for the static friction. And the direction of static friction is whatever direction is required to prevent the object from slipping. So this frog wants to slip down the surface. So there's a Fs of the surface on the frog in this case. Oh, this is object. Surface, which points in the opposite direction that the frog would want to slip. So let's do a poll about this green Corolla here. So a car is parked on a flat horizontal pavement. Which of the following forces should be added to the force diagram of the car? Is it A, gravity, B, normal force, C, static friction, D, all of the above, all three of these, or E, A and B, but not C? If you're going to draw your force diagram, what should you put? Oops, that's right. All right, there we go. I've just launched a poll. Okay. Let's give you another 5 seconds. What do you think? 5, 4, 3, 2, 1. Okay, 90% voting, so that's good. So it was sort of a toss-up between either all of these forces are on the force diagram, or A and B, the gravity and the normal force, but not the static friction. So I actually, what I was looking for here was E. And the reason for that is that once you draw the normal force of the surface on the car, and you draw the force of gravity of the earth on the car, so they're both on the car, you could draw a static friction force, but which way would you draw it, right? You need to have acceleration equals 0 since it's just sitting there. So there's that implies that there are no horizontal forces. Another way of putting this is that all of the horizontal forces are 0. F sub S is 0, you could say. So there is static friction, but it's 0. So maybe that's what you're thinking. But if a force is, you know it's equal to 0, you just don't draw it on the force diagram. So this is a bit of a tricky one. It's like it's there, but it's not there. There's a maximum static friction force. There's a limit to how big static friction can get. If you push hard enough, an object will slip and start to move. In other words, the static friction has a maximum possible size. So, and Fs max is equal to, so many experiments have shown that the following approximate relation usually holds, is that Fs max is equal to something times the normal force. And once again, this is a dimensionless coefficient, okay, which you look up in some table somewhere. But it's different than the coefficient of kinetic friction. So we have this equation, and I want to see if you can use it. I'm going to give you a couple of polls here. Here's a wooden block that has a mass, okay, so this is a little bit better. Instead of saying it weighs 100 newtons, we should say it has a mass of 10.2 kilograms, so the force of gravity of the Earth on the block is 100 newtons. It weighs 100 newtons. The block is sitting stationary on a smooth horizontal concrete surface. The coefficient of static friction between the wood and concrete is 0.2. A 5 Newton horizontal force is applied to the block, pushing it towards the right, but the block does not move. What is the force of static friction of the surface on the block? Is it 100 newtons to the left, 20 newtons to the left, 5 newtons to the left, 20 newtons to the right, or 5 newtons to the right? The lights are on. This is a tricky one. Let me give you guys another 10 seconds, and then I want to discuss the results that are coming in. 5, 4, 3, 2, 1. So most people were answering B. So B, it turns out to be 100 times 0.2 is 20 newtons to the left, but I think that's going to give an unbalanced force. I don't think that can possibly be right. So what I'm going to do is I'm going to draw a force diagram of the block. That's the only way you can do it. And there is no equation for the static friction force. It's like normal force or tension. There's no fixed equation for it. You just have to use your forces. So there's normal force, again, of the surface on the block. You've got this pushing force, F, of the hand on the block, which is equal to the 5 newtons. You've got the gravity force, F sub G, of the Earth on the block. And you've got this backwards force, F, static friction of the surface on the block, like that. And I would just say that acceleration is 0, it's sitting there. And so the forces in the x direction, if we want to set up a x-axis and a y-axis, are equal to 0. And that's going to be F minus F sub s. So F equals F sub s is 5 newtons, and it's to the left. Did you follow that? So most of you got that one wrong, but if you did answer C, that's great. So let's do another question similar. This is your redemption question. Relaunch the polling here. You've got now same exact situation, but the question is not what is the force. Oops, maybe I should put there. Let's forget about this one. You're pushing it towards the right, but it still doesn't move. Okay. So the question is, forget about that sentence, what is the magnitude of the maximum horizontal force you can exert on the block and have the block remain stationary? I think this is what you guys were trying to answer last time. Because there is an equation for the maximum static friction force, right? 10 seconds to click in, and I'm going to show you the answers. Five seconds. Turn it. Okay. So 92% of you think that it's 20 newtons. That is correct. You got it. So in this case, it's the same force diagram as before. We can look at it, which looked like that. Now, in this case, though, it's not 5 newtons. So what you do is you say that the sum of the y forces is 0. That's equal to the normal force minus Fg. So that implies the normal force equals Fg, which was 100 newtons. And then the sum of the x forces equals 0. So again, what that means is that the pushing force is equal to Fs. In this case, now it's Fs max. So that's mu sub s times the normal force. So it's equal to 0.2 times 100. And that's how you get the 20 newtons. F equals 20 newtons. So that was good. Okay. I was going to go through a few more things. I think I will quickly note that there are these tables. I'm running out of time a little bit. I'm just going to do a little demo. There are tables you can look up of typical coefficients of friction. For example, rubber on concrete, the static friction, coefficient of static friction is 1, sort of at its maximum. This coefficient of kinetic friction is 0.8, it's less. Steel on steel, coefficient of static friction is 0.8. Kinetic friction, if it's sliding, 0.6. That's if it's dry. If it's wet, you get a much lower coefficient of friction. That's why it's slippery. There's wood on wood, 0.5, 0.2. Wood on snow, 0.12 for static and 0.06 for sliding, so it's very low. Ice on ice, either static friction 0.1 or 0.03. So as these go down, things get more and more slippery. And I think that is it. Thank you very much. We'll come back on Monday and we're going to finish up chapter 4 and get you ready for the or no, we're going to continue on with chapter 4, and I'll see you then. I'm going to turn off the recorder, then I'll go to the hands.